Today's lesson is going to introduce us to topics 4.2 and 4.3, which covers traveling waves and wave characteristics. I'm not going to go over the various objectives for 4.2 and 4.3, but they're presented here as well as in the guidebook, which you can all look up. There isn't much in the way of formula in topics 4.2. There's just the wave formula that says the speed of the wave, they use the letter C in this case, is equal to the frequency of the wave times the wavelength. Okay, for some reason they feel that this is an important derivation that you need to know, and so under guidance we have that you're expected to be able to derive this. It's also important to note the second point of guidance, that you need to memorize the electromagnetic spectrum. Okay. Topic 4.3 gets into different aspects of waves, wave characteristics, and how to visualize them. There's three formulas in here, which we'll talk about primarily in the next set of slides, but they're given here. Okay. First off, we're going to start off with a bunch of definitions. We've already talked about frequency, period, amplitude, and equilibrium when we talked about simple harmonic motion and oscillations. All of those definitions still apply. Now we have a few more definitions that we need to work with, and that's wavelength, which is the distance that the wave travels in one period, measured in meters. The word medium, okay, is the substance that the wave requires to propagate or travel through. Sound, for instance, travels through air. The wave on a string clearly travels through the wave, or the slinky, or water. Okay, those are examples of mediums. The only wave that we're aware of that doesn't require a medium would be electromagnetic waves, and with the recent discovery, also gravitational waves. Okay. We also need to know the difference between a transverse wave and a longitudinal wave, which I'll talk about in the upcoming slides. Okay, a transverse wave is most of the waves that we encounter. Okay, in particular, you need to know that light waves are transverse electromagnetic waves. So a transverse wave has the motion of the medium, or motion of the particles, going perpendicular to the direction that the wave travels in. In this case, the wave travels from the red block on the left and travels to the right. So that's the direction of the energy of the wave. That's what actually travels, the energy of the wave. Okay. However, the particles in this case are moving up and down. So that's perpendicular to the wave motion. In the case of electromagnetic waves, although there's no medium, the electric field and the magnetic field go up and down, or perpendicular to the direction of travel. A longitudinal wave, in particular sound waves, are longitudinal waves. Those are the primary waves. Another example might be earthquakes. The P wave, I believe it is also a longitudinal wave. Okay, and in this case, the sound is again moving from the left side of the screen to the right side of the screen. And so what we have here are the little atoms of air. They tend to vibrate in the same direction. So they're also vibrating left to right, left to right. Instead of moving perpendicular, the particles move parallel to the wave motion. Okay. If I had a vacuum, like for instance in outer space, I would not be able to hear anything because there's no particles that hits the next particle and the next particle and the next particle. So that's why waves need a medium, with the exception of the electromagnetic and gravitational waves. When we talk about longitudinal waves, instead of talking about wave crests and wave troughs, because it doesn't seem to make sense, we talk about compression points and rarefaction points. Okay, compression points are where the particles in the medium are squished closer together, and rarefaction points are areas in the medium where the particles are stretched further apart than normal. Okay, these allow us to calculate wavelengths, because moving from the center of one compression to the next compression gives us the wavelength. Okay. However, they do not correspond exactly with wave crests and wave troughs. They actually correspond to the equilibrium crossings. Okay, the compression points and rarefaction points correspond to the equilibrium going with a negative slope, and then equilibrium with the positive slope. Okay, but it does still allow us to calculate wavelength. So that brings me to the wave equation, which is the primary equation in topic 4.2. Okay, and last year we talked about it as being v equals f lambda. Velocity is equal to frequency times wavelength. Okay, and this derivation comes strictly from the definitions from frequency and wavelength. It's not a complicated definition, which is why it surprises me that the IB wants us to know it. So it gives us that velocity is equal to frequency times wavelength. Last year, the mnemonic that we used was visit the friendly llama. Okay, and for light, because light travels at a speed of 3 times 10 to the 8th meters per second, we use the letter C. Light allows us to see the friendly llama. Okay, so it also requires us to memorize the electromagnetic spectrum, not just necessarily in the order that of the waves. Okay, most of us have that down, as well as Roy G. Biv for the visible spectrum. Okay, but it does help you to know that the types of frequencies and the regions of the electromagnetic spectrum. There's a mnemonic that we use in biotech primarily, and it says that Ray's mother is visible under X-ray glasses. There are many other mnemonics out there if you want to look in the internet for them and find one that works for you. But R stands for radio waves, then microwaves, then infrared. Okay, and that's why you know that red has longer wavelengths. Okay, and then the visible light, ultraviolet, X-rays, and gamma rays. Okay, so again, Roy G. Biv, the V is violet. That's why we have ultraviolet, then X-rays, then gamma rays. It's also useful to get a sense for the wavelengths involved. Once you know wavelengths, you can tell what the frequency is using the wave equation, and energy, which we'll talk about next year. Okay, so spend some time and try and memorize these numbers, in particular for visible light. Remember that it's 400 nanometers on the low side, up to about 800 nanometers on the high side. So it's a very small band for visible light. Okay, so why are they electromagnetic waves? Okay, they're electromagnetic waves because they have both a magnetic field and an electric field, and these two fields are oscillating in simple harmonic motion, okay, or in a sine wave, cosine wave. They're perpendicular to each other. So if my electric field is traveling in this direction, my magnetic field would be traveling perpendicular to that, and they would both be perpendicular to the direction of travel, which in this case would be towards the screen. Okay, and so that's what an electromagnetic wave is. Okay, and the other thing to know is that electromagnetic waves, or actually any transverse waves, but primarily electromagnetic, and the electromagnetic waves can be polarized. What that means is I'm restricting the electric field to a single plane only, okay? And by definition then, my magnetic field is also being limited to one plane only, okay? So, polarizing a wave basically restricts us to one plane. Normally, most light is unpolarized, meaning it travels in many different planes. If the light is still traveling towards you, it could be, the electric field can be vertical, rotated 45, rotated minus 45, or rotated 90, or any infinite number of possibilities, as long as it's still coming towards you. Okay, but by restricting us to one plane only, I can use a polarizer to say, no, I don't want all of these planes. I only want one plane. Okay, and that allows us to do various things. There's a video that I want you to watch attached to that describes polarization a little bit better. And that's a separate video on Google Classroom. Okay, so the speed of light, okay, all electromagnetic waves travel at the speed of light, which happens to be 3 times 10 to the 8th meters per second in a vacuum. And air happens to be very, very close to the same speed, okay? But because of relativity, which you may learn about next year, nothing travels faster than the speed of light. Okay, light can travel slower through various mediums like water or glass, but it doesn't travel faster. Okay, even if you're in a car going at half the speed of light and then you turn on the lights, the light still only travels at the speed of light. And this is all because of relativity, which is all much too complicated to get into in this lecture. Then we have different wave representations. How do we visualize a wave? One way is to use wave fronts, which is pretty much just the crest of the wave, okay? And it travels away from, in this case, from the source, that the origin of all these circles. And that, therefore, the distance between the fronts gives us the wavelength, okay? Wave rays are similar to light rays, okay? It's the direction of velocity for the wave. And it's important to realize that the wave ray must be perpendicular to the wave front. And in this case, the wave ray is useful for measuring angles. It's kind of like the red line in the picture above, okay? And so this is also very similar to what we had to do for electric field versus electric potentials, okay, as well as gravitational field, gravitational potentials, okay. And that brings me to Huygens principle, okay. In this picture we had the blue and red picture on the top, okay. We show refraction occurring at a medium boundary, okay. And Christian Huygens, who was alive around the same time as Isaac Newton, and was probably equally as brilliant, but was shortchanged in a number of ways. But Huygens believed that light was a wave. Newton believed light was a particle, and Newton ended up winning that battle, partially because, I want to say, he lived in London and England, which was the center of the Royal College, and so he won based on political aspects. Okay. Later, in the 17th century, it was proved that Huygens was right and that light was a wave. Until the early 2000s, 1900s, when Einstein came along and showed that Newton was right. And then there's this whole battle between whether light was a wave and light was a particle. And it turns out they're both right. Okay. But Huygens' principle basically states that every point, think of an infinite number of them, and anytime you think of an infinite number, you should think, oh, I should probably also involve calculus. But that every point on a wave front is itself the source of a spherical wave. And the superposition or sum of those infinite wavelet fronts is the wave itself. Okay, so here's a couple of examples. Okay, a wave is moving outwards in the top left radially. And so if I think of the wave as being the smaller one, in a certain time later, all the little points have expanded, and I add them up, and I get where the wave is at a certain amount of time later. Okay, same with if it's a parallel wave, okay, or a linear wave front, okay, which is the lower right-hand side. Okay, and so why is that important? Okay, that's important because it helps explain why waves actually refract when they hit a boundary, okay? Or it explains why waves diffract, which is the lower left-hand side, when they encounter boundaries or encounter objects. Why do waves bend around the object instead of just going straight? Okay, thank you very much.